So as a recap for the last couple lectures, we talked a lot about value functions and Q functions. We'll talk about them more today. And as a reminder, value functions and Q functions are representing our sum of future expected rewards, starting at some state. And value functions will be future expected rewards to start a state to follow policies. And the Q function is if you start the state, take an action, and then follow it. So you can write these down mathematically as expected future rewards. And you've seen these diagrams a couple times where you can think about value as the sum of future rewards from the state, and the Q function as the sum of future rewards from the state. We've talked about a couple methods so far. The first method that we talked about was policy gradient, where we alternate between collecting data and improving our policies. You can think of it as trying to sample for our policies and increasing the log likelihood of actions that have a higher reward in the future, where we subtract the baseline in order to encourage the policies to do more of the above average things than it did before and less of the below average things. We then started to talk about actor-critic methods, and in this part we introduced an additional step of this loop where we are first going to estimate the expected future reward for our policies and use that to improve the policy. So we had this revised form for our gradients for our policies where we are still taking samples but increasing the likelihood on actions that we think are good and decreasing the likelihood on actions that we think are bad. And so these are the methods that we've talked about so far. Last lecture focused a lot on how to do this actor-critic algorithm in an off-policy way. So instead of only using the data from the current iteration, trying to be able to use all of the past data from all past iterations. And to do that, we needed to be able to estimate a Q function from past policy data. And to do that, we can use a neural network, pass as input a state and action, and output the value. And we derived this equation that's defining the Q function recursively, where we can think of the sum of future rewards as the reward of the first time step plus the Q function starting at the next state and action. We found that this equation holds for any state and action, and that means that we can use previous state action and next state pairs in order to try to learn a Q function. And specifically, the way that we did that is we would sample a state action next state from our buffer of previous data. Then we'll sample a next action from the current policies rather than from the past policies. And then we will try to do supervised learning on these targets, where the targets are using our current estimate of the Q function for our policy, and we pass as input the state, the action, the next state, and the next action that the sample is. So once we formulate this objective using our bootstrap values, then we can do supervised learning with an LP law to try to map the Q function. And we also talk about for these YIs to be accurate, you need to have sufficient coverage in your data set to cover actions that your newest policy makes. So today we're going to be covering value-based RL methods, and specifically we'll be talking about what I think arguably was the very first deep reinforcement learning method, and it was based on the Q-learning algorithm. And so we'll be talking about Q-learning, and then we'll also be talking about how to implement Q-learning in practice, how to make it stable. And the goal for today is to think about how Q functions relate to policies, how to do RL without learning an explicit policy, and how to stabilize Q-learning if you're actually doing it. Cool. So we're going to start out with a thought exercise and a question for all of you to think about. So say we have some policies, and for your policy, you have a pretty good estimate of the Q function. And as a reminder, I'll put the definition of Q values up here, where it's the future rewards for a state and action. And an object that we're going to be thinking about a lot today is if you have some estimate of the Q function in this case for a policy, then one thing you could do is you could try to, instead of following some policy that you've already learned, you could potentially formulate a policy by choosing the action that maximizes your c-value. So if you have a bunch of different candidate actions at a given state, instead of following your policy, you could pick the candidate action that has the highest c-value. So to continue on this thought exercise, we'll define a policy that does exactly that. That policy has a probability of 1 for taking the action that maximizes the p-value and has a probability of 0 otherwise. This is just a deterministic policy that always follows what the p-value is telling you is the best. And then we'll look at this in the context of an example. So say that we have some 2D navigation problems. We're going to be starting somewhere in this blue box, and our goal is to reach to the star. You can move in 2D. The reward is 1 at the star and 0 elsewhere, so very simple. And let's say that our current policy always goes to the right. And as one additional point of detail, if you're going to move up, it takes 1 time step to move about this distance, and it takes about 2 time steps to move this distance. So my question for you is, if you define this new policy, you have this current policy that always goes right. You have an accurate estimate of the p-values for that policy. If you define this new policy, is that better than the current policy? Is it worse than the current policy? Is it the same as the current policy? Is it the optimal policy? And why or why not? So I'll give you, well, first, any questions about this example? Okay, so I'll give you a few minutes to talk to your neighbor about these questions, and then we'll come back and talk through the answers. It seems like people are talking a little bit less, so maybe we can come back. Who wants to share their thoughts? Yeah? So let's summarize that, and then we'll talk about whether it's the optimal policy. So to summarize, the old policy is going right, and so that is not optimal, because if you're starting here, then you're not actually going to hit the star. And if you think about what q pi is for the old policy, kind of everything in this region right here is going to have a q pi equal to 1 for all of these states and actions. Also and then if you start to think about what q pi looks like right here, this is actually where it will, take that back. V pi is equal to 1 for everything in this row. It actually depends a little bit on the action, what the q function actually is. For this row, if the action is the same as the policy, that's to move right, then the q value is 1. If it actually does something else, if it goes like up, for example, then it might actually miss the star if it follows the policy after taking that action. Now, if we look at this row, for this row, q pi of all the states in this row for the action of going right is going to be 0. But then if you look at the q pi for all the states here for the action of going up, what is the q value for that? What is q pi? 1. Cool. And so that's because if we follow up and then follow the policy, we'll have a reward of 1. And then lastly, if we go to this row, if we have f and then going up, what is the q value? 0. Cool. And so what this means is that we're going to get the new policy. What it's going to do is it's going to be going right here. And then for everything in this row, it will be going up because it's going to be choosing the action that has the maximum value of q pi. But then for this row, all of the q values are 0 because all of the q values for the next one are also 0. And so if you default to the previous behavior, it'll stay going to the right. And does anyone want to discuss the second question, like is this the optimal policy? Yeah, so this policy, the new policy is better than the old one, but it's not the optimal policy because in these states, the optimal, like the best policy should be the one that also is going up in order to get to success. Yeah, so the question was if we iterate this and do it a couple times, this will become the optimal policy, right? And yes, you're a couple slides ahead, but we'll talk about doing this iteratively. Yeah, so we can get a reward of 1. The question was, why is this not the optimal policy? So we'll get a reward of 1 here, which is great. But if we're starting at this initial state, we actually will just keep on going right. We won't go up after defining this new policy. And so therefore, it's not going to get a reward of 1 from all states. Yeah, so the question is there a sense of, like, if you're getting closer to the star, the Q would be higher versus not? I actually didn't explicitly define this, but if you have a discount factor that is below 1, then it will get higher as you get closer. Everything I've shown here is with a discount factor of 1 for simplicity. But if you use a discount factor of like 0.9, for example, then the Q value here would be 1, then it would be 0.9 here, then 0.8 here, 0.7 here, and so forth. And then it would be, it would still be like 0 for this entire row, just because because you're kind of still somewhat of a slice. The other thing potentially to note here is that if your reward was denser, if like the reward function instead of being 1 at the star and 0 elsewhere, if it was, for example, the negative distance to the star, then you would actually, I won't go through that, on the board, but if you go through that example, you'll actually see that even in a single step, starting from this policy, you would actually get a policy that goes to the star from all states. The question is, if I wanted to get the optimal policy, I would need to iteratively do this and reconsider the Q pi for the latest policy every time. So yeah, that's correct. Yeah, so in this example, the question is it always better? In this example, the new policy was better than the current policy, and this is actually always going to be the case. So it's always going to be at least as good as the previous policy. And it's never going to, well, assuming that Q pi is accurate, it's always going to be as good. It's never going to be worse. And now if Q pi is already the optimal policy, then it will be the same. This is starting to think about, like, can we actually start omitting policies? So Q is the expected reward. When we do this argmax, we're going to be taking the best action from state S if you then follow the policy afterwards. And this is going to be at least as good as any action that the policy would have taken. And regardless of what the policy is, this is going to be, yeah, at least as good as what that policy would have taken. You can do that because it's taking the action that has the maximum expected reward. So potentially we could actually just forget using policies and just do this, rather than actually explicitly learning a neural network for the policy. And so what this looks like as an iterative algorithm is we would run our policy to collect data, then we would fit a model to estimate Q pi according to that latest batch of data. You could also do this in an off-policy way, like we talked about in the last lecture. And then to improve your policy, you can just define the policy to be the policy that maximizes the Q pi. And then once you define that new policy, you can collect some new data and then estimate again Q pi, but in this case Q pi for your new policy and not your old policy. The policy pi is equal to this, and so we're not learning a neural network for the policy pi. We're not explicitly representing it as a model, but it's helpful to have some notation to refer to the system. The only neural network here, the only model here is the C++. Yeah, so the question is, how do we generalize this to continuous actions or more expressive action spaces? So this is generally going to be easiest when you have kind of a discrete set of actions that you might take, like going up, going to the right. If you have continuous actions, you actually can still use this algorithm. Although you need to figure out how to perform that max operation. There's a couple ways that you could conceivably run this operation right here. In principle, you can use something like gradient descent, although that turns out not to work very well. You can potentially, there's a variety of reasons why it cannot work very well. And if your actions are not very high dimensional, then you can, it might actually be better just to simply try to sample a bunch of different actions and pick the one that has the highest p-value. You can also, there's other kind of sampling-based optimization algorithms where you can iteratively sample and refine your estimate from there. So there's a couple of things you can do there. If you have a discrete action space that's like text, for example, in principle you could do some sort of like discrete search over things where the Q value is is what you're trying to maximize in that search. Yeah, how does this work in cases where the rewards are very sparse? So we saw one example where the rewards are sparse, and it can still work in this scenario. The thing that you need to be aware of when the rewards are sparse is that you may need to do this loop of refitting the policy potentially a large number of times, because each time you do this, you're actually, like the first time we only got a good policy here, and now if this environment was much bigger, that means that you need to kind of keep on doing it as you go down. And what is often referred to as a backup, you're sort of backing up the reward from here to the other state, and you'll need to do those backups for as long as essentially almost for as long as the horizon of the problem is. So you just need to make sure that you're doing many iterations. Okay. Cool. So let's see. We can write this down as an algorithm. And so we can take our off-policy actor-critic algorithm that is fitting Q pi, and then instead of using this policy gradient update, simply define a new policy that that's taking actions according to. You can think of this as really having two key steps, like what we talked about. One is estimating Q pi. This is often referred to as policy evaluation, because you're learning what the values are for a policy. And note that you can do multiple gradient steps here, because this isn't like on policy. We're just trying to fit our target. And then the second step is improving our policy. So you refer to it as policy improvement. And this sort of two-step iterative procedure is often called policy iteration. It's kind of on the way to an algorithm like this. Cool. So to write this out on the board, what this looks like is having a first step where you collect data. Oftentimes you might collect data from pi. It could actually potentially be from some other policy. Then you have a next step where you're going to try to fit your estimated Q function for that policy. And that you can use the targets that we defined in the last lecture of R of SA plus gamma times Q, where these are from the buffer and this is sampled from our policy. And then lastly, we'll improve our policy by defining a new policy as being 1 if the action is maximizing P value and 0 otherwise. The question is this policy deterministic? Yes, this policy is deterministic. This is actually one reason why you might not want to collect data from this policy, because you're not going to have that much diversity in your actions. And we'll talk in a couple slides about what policy we might want to collect data from. Yeah, so the question is, when we're fitting these targets, why are we sampling from A prime, and why not do a maximum over action? Or an average. So There's a couple things here. So first, you can do an average and sample multiple times, and that can give you a better estimate of the target value. The second thing is that you can actually, instead of sampling this from pi, you can actually do this improvement step in the Q function target itself. So you can actually, instead of defining yi this way, you could consider a target for your Q function to be the reward plus gamma times the max over A prime of QS. And what this looks like is something like this. And this actually is what gets us here. One way to think about this is a couple ways to think about this. The first is that these targets are actually your Q values for your new policy. So you're actually, you're already putting the improvement steps in your Q function update, and you're actually learning the Q values associated with the new policy that you're going to be defining. And there's actually another way to look at this as well. So we previously defined this equation that's true for all states and actions. So we defined that the Q function is equal to the reward plus the Q function at the next state. This is true for all states and actions, and it's actually also is true for any policy, including the optimal policy. And you can actually write down another equation that is specifically for the optimal policy. And in particular, we know that the optimal policy is always going to be picking the actions that maximize our future rewards. And the optimal policy is always going to be, the action that it picks is always going to be the one that maximizes the Q values. And so we can write down an equation that holds just for the optimal policy, which is the same equation as the one there, except instead of an expectation over the next action, it's a maximization over the next action. So what that looks like is we're defining the Q function as the reward at the current time step plus the sum of future rewards. And for that sum of future rewards, we have some expectation over the next state that will happen. And then, because we know that the optimal policy or the best policy is going to be taking the action that is maximizing the Q value, then we can write this as the max of Q at the next state. Yeah, so the question is, why are we talking all about Q and why not V? So you can actually also write down these equations for V in like a very similar way. The thing that's very nice about Q is that we can actually get a policy out of Q. So we can, if we know what Q is, then we can do this argmax over action to get a policy that's better than our previous policy. Whereas with the value function, if we only know V of S, then we don't know which action will lead to higher future rewards. In principle, with the value function, you could try to do some sort of look ahead. Like if you have a sense for what the dynamics are, you could try to then, you could try to predict what S prime is and pick actions that are maximizing that. And so what that would look like is trying to like pick actions that lead to an expectation a high future value. So you could in principle do something like this with V, but we don't know what these dynamics are, and we can't necessarily predict what the next state will be as a consequence of our action. And so in general, it's a lot harder to get a policy out of a value function than it is to improve our policy ultimately. with the value function than it is with the Q function. So now going back to this equation, this is true for the optimal policy. And we write Q for the optimal policy here, where I'm writing pi star as the optimal policy. And if you look at our update right here, we're trying to fit a Q function that is that's predicting this. And essentially, with this equation, you can think about it as this update as actually trying to make this equation true. So we're trying to make the left side of the equation equal to the right side of the equation. And when this equation is true, that means our policy is the optimal. So essentially, one way to think about Q-learning is that when we're optimizing step 3, we're trying to find a Q function such that it satisfies this equation, which is only true for the optimal policy. Yeah, sorry. This is like it's an only. So this only holds for the optimal policy, and if you have the optimal policy, then this. Yeah, great question. So the question is, if we have really good estimates of Q, will this converge? We'll talk about this in 1 minute. So let's first just talk about some terminology really quick. Reinforcement learning has a ton of terminology. It's useful to know some of it so that if someone's talking to you about reinforcement learning or you're reading a paper, you know what they're talking about. This first equation is often referred to as the Bellman equation. It's a very useful object, and it's what we were using to try to do policy evaluation for a policy. And the second equation is called the Bellman optimality equation because it's specifically for optimal policy. Sometimes people also informally might call the second one a Bellman equation as well. But yeah, officially the first one is Bellman equation, the second one is Bellman optimality equation. You can derive ones that are equations like this that are also for the value function b instead of the Q function, and people often also refer to those as Bellman equation and Bellman optimality. Okay, so getting back to the question, if we do this iteratively, will we converge to the optimal policy? There's good news and bad news here. The good news is that if you're in a very simple setting, where you can actually store all of your Q values in a table for every single state and action, this would be for a very small, discrete state and action space. And if you have sufficient exploration, then this algorithm will converge. So that's the good news. The bad news is that basically in any other scenario, it is not guaranteed to converge. And you can construct scenarios when it diverges, even with just linear Q functions, which is kind of sad. I guess the flip side of that is even though it can diverge in scenarios, it can be made to work very well. And we'll see some examples of it working very well at the end of the lecture. Yeah, so the question is what does this if mean? What does the statement mean? And it is a bit vague. So specifically, it doesn't necessarily have to do with the accuracy of your Q values, because you're actually going to be fitting your Q values through this process. It's more a statement of the size of your state and action space, and if it's small enough that you can maintain this table. And there's also a condition on exploration where you actually need to have full coverage of the state and actions in your data set. Then it will converge. Okay. So one note about this is Q-learning is off policy. And in particular, this equation holds for all states and actions. And it means that we don't have to have the actions coming from our current policy. And in particular, it might actually make a lot of sense for it to be broader than our current policy, because we're going to be doing this maximization over our Q values. And so when we do this maximization, we're going to be considering a lot of different possible actions. And if we have a discrete action space, we might actually just consider all of the possible actions. And when we do that, we would want our Q values to be accurate when we're considering all of them. And if there's one action that we haven't collected data for, that we're going to be considering in this maximization, it might be erroneously high because we didn't collect any data for it. And then you'll get an inaccurate target value when you're fitting your Q. And so instead of collecting data from our current policy, it'd be useful to collect data from some exploration policy, and specifically a policy that's selecting a broader set of actions than our deterministic policy. So we want coverage for a lot of different actions, specifically for this term. And there's a couple choices here. One choice is to mostly follow our policy, most of the time, but with some small probability, take a completely random action. And so what that would look like is a policy that, with some probability, I would say maybe you can write it as like, take a random action with probability epsilon, and follow, maybe we can call this pi exploration, and follow your current policy with probability 1 minus epsilon. And you can write that out slightly more formally up here. And this can be a good choice because it means that when you take an action uniformly at random, it means that you'll get very good coverage of the actions that you consider. And oftentimes as you proceed through training, you might start with a larger epsilon, so that you have more exploration at the beginning of training. And then as your policy is getting better, and as you're getting a better estimate of your Q function, you can then make this smaller and explore less as you go through training. This is called epsilon greedy, because you're being greedy some of the time, and epsilon probability of the time you're not being greedy and just taking a random. Okay, and then another choice that's also somewhat reasonable, although a little bit more complicated, is to take actions with probability that is proportional to the Q-value. And so if you have actions that have a higher Q-value, then take those actions more frequently, and if you have actions with lower probability, then take those actions less frequently. One way to write this is you could exponentiate your Q-values so that they're all positive, and then normalize in order to get a probability distribution over X. Sometimes this is called Boltzmann exploration, named after the Boltzmann distribution, where you exponentiate and not. Yeah, so the question is, how do you, it's straightforward to do this with discrete actions. How do you do these kinds of approaches when you have continuous actions? The first one is indeed a lot more common with discrete actions. You could still do something like this with continuous actions, but you would need to define some uniform-ish distribution over your continuous actions. And for that, you would need some sort of range or something. Instead, you could also use like a Gaussian distribution with a wide standard deviation in principle, where you sample from that. I think in continuous action spaces, this second option is a bit more common. In terms of sampling from it, off the top of my head, I actually can't remember the details of how you would sample from this, but we can post on Ed after. It's possible that the way that you do it is actually just to try to fit a policy. But yeah, we can talk about it after. Okay, so putting the pieces together, what a full Q-learning algorithm looks like is we'll collect data using some policy. We'll add that data to our replay buffer. Then we will sample a batch of data from our replay buffer uniformly, and it's useful to sample a batch kind of separately from what we just collected, so that we are decorrelating and sampling IID from our replay buffer. And then we will update our Q function by taking the gradient of the L2 loss with respect to these targets. And so if you write that out, you'll get a gradient that looks like this, where, if you're taking the L2 loss, then on the inside, this is the inside of the L2 loss, and then you use the chain rule to get the second term right here that's back propagating into your parameter. You can repeat these multiple times. So you can actually kind of take multiple gradient steps after collecting a batch of data. In practice, it's actually pretty common to set k equals to 1, but it's more efficient, you're going to be more data efficient if you have a larger k to take more gradient steps for a given batch of data. And then you also iterate this process. After you're done taking these k gradient steps, then you can collect some more data and repeat. Yeah, so the question was, if you're collecting data from any policy, wouldn't that be less optimal than like using a good policy or at least using your current policy? Yeah. So the reason why you might use a different policy is specifically to learn a more accurate Q function, and so it's actually going to help you learn a more optimal policy later. And essentially, there's this trade-off between collecting less optimal data at the beginning to help you be better later on. And one way to think about this is if you are, say your reinforcement learning agent is trying to help you pick a restaurant, if you haven't really explored that many restaurants to know what is a good restaurant, then at the beginning, probably you want to explore and actually try things, even restaurants that might be suboptimal, in order to get a good estimate of like what good restaurants are for a particular person. And then later on, once you have a good Q function, once you have a good estimate for what good restaurants are, then you might want to then explore less. So kind of visually what this looks like is you have some environment, you'll initialize your replay buffer as empty, and then at this first step, you'll run your policy, like the epsilon greedy policy, that's exploring in the environment. You'll then get some transitions that you put into your replay buffer. And then for this part, you'll then use your replay buffer to update your Q function on the data that you see, with the goal of trying to get something that is not saying the Q function of the optimal. So the question is, when we combine this with one, like, do we still call this off policy because we are collecting data potentially from a policy that's very similar to our current policy? Because we're using a replay buffer of essentially all of our past experience, when we do these updates, it's referred to as off policies. That doesn't mean that like none of the data is from our current policy. So some of the data in the replay buffer will be from the current policy, but essentially what off policy means is that you're not only using that data, you're also using data from other policies. In practice, what is the sum policy? Yeah, so in practice, it's exactly what we talked about on the last slide. So it would either be something like epsilon greedy, where with some small probability you're taking a random action and otherwise following the policy, or something where you're taking actions in proportion to their Q. And this might actually, as we talked about, it might actually change during training. You might actually change the epsilon during training so that you're doing more exploration at the beginning and less exploration later on. Yeah, so the question is, are we resetting our learning as Q iteration? Oftentimes you'll keep your old Q parameters around, kind of warm start them and keep on training on top of them. One important thing, so the result of this algorithm is Q, and then to extract a policy out of that, the final policy that you would then deploy is a policy that is acting according to, essentially just be acting greedily, where it's taking the actions that maximize your Q. Oh, so if the size of the replay buffer is 1, then one data point, then that would be on policy. So if it's tiny, then that's fully on policy. In practice, this replay buffer is a lot larger. Sorry. Right. If the replay buffer size is 1, if this policy is not the same as this, then that's still off policy because the policy is different. Yeah, it's a good point. So yeah, this policy might be different from the one that you're actually on. Yeah, so how do we manage our replay buffer, make sure that we're not oversampling states and so forth? This is generally, it's actually an important consideration with Q-learning algorithms, and usually you will discard old data, so you'll have like a first in, first out principle where this buffer is not infinitely large. Oftentimes with Q-learning it is pretty large, but you will, you can just pick a fixed size, and then once you have filled it to that size, start discarding data and discard the oldest data first. One other consideration is that at the very beginning of training, the replay buffer might be very small. Sometimes to handle that, you might try to collect more data the very first iteration to pre-populate it. There are also algorithms that we won't quite cover that do asynchronous data collection and updates, because data collection takes time, updating a neural network takes time, and so you could actually have some threads that are actually adding to the replay buffer and other threads that are running updates on your queue function. With those asynchronous algorithms, it's actually especially important to think about how the replay buffer is managed so that you're not running like 1,000 gradient steps on one data point and one gradient step on another data point. Cool. So that's queue learning. Let's talk a little bit about what happens in practice when you use these methods. So we talked about how queue learning can diverge, and in general, when you run queue learning with neural networks, it can be unstable. And one of the reasons for that is you have this moving target, this max of Q, and it means that our optimization process is very non-stationary, especially as K is 1. And one trick is to try to slow down how often you change the target. So instead of having these targets change every single time you change your parameters, one idea is you could freeze the parameters of your target network and only update them kind of periodically, only update them once every 100 gradient steps or something like that. So what this looks like is we can save a separate neural network, another copy of our Q function parameters. We'll call this 5 prime. And when we save this out, then just for this target right here, we can use these new parameters, Q5 prime, in our target. These parameters will be frozen, and so it means that inside this inner loop, the labels will not change. And so this inner loop is essentially going to be doing supervised learning with some data being added to the replay buffer. And this would be a lot more stable. Supervised learning is a lot more stable, generally. And then only periodically then update our target network parameters to be the same as our latest Q function. So once you use a target network, this is referred to as the DQN algorithm. It was introduced in 2013. It was basically the first DeepRL method, at least in my opinion. And they found that you could actually train neural networks to play a variety of different Atari games. And it was, one of the first examples of using reinforcement learning to train neural networks to do a pretty complicated task. And they were actually training it directly from the pixel observation from the game. And prior to that, a lot of the reinforcement learning examples were on very toy settings or very low dimensional settings or something like that. If you save two tables of two values, will that be the same as this? Yeah, so that's actually not quite the case because you will actually be collecting new data in this loop. And so you can't just store all the key values. You actually do have to store the parameters so that you can then compute the key values for the new data that you collected, the target key values for the new data. So you can't just store the key values. You have to store it. Cool. And so this is one of the algorithms that you'll implement in almost two. Okay, so that's the first trick, is use a target network that you only periodically update. There's two more things that make Q learning work a lot better. And the first one is actually looking at the accuracy of the Q value. So if you plot the reward over training, the reward goes up, so that's good. This is a reward on the game of Breakout and the game of Pizza. And if you also plot the key values over the course of training, they're also going up. And so that's actually what you expect, because the key value is representing your average reward. So that's good. One other thing to note, actually, is like a practical tip, is when you're looking at the loss functions on your p-values during training, when you train with D2N, the loss values will actually often go up through training. This is sometimes a little bit alarming because you're used to loss values going down, but the reason for that is you're collecting new data, and that new data has higher p-values, and so the scale of your loss function is increasing throughout training. And at the very beginning, if you're getting like 0 reward everywhere, it might be very easy to get a loss function. So yeah, don't be alarmed if your loss function is going up. Sometimes that means that the algorithm or the policy is starting to work. So cool, this looks pretty good. As it predicted Q increases, so does the return. You can also look at the value over training, and you see that right in the first case, the values right here are fairly uniform. But once you're in a state where you like really have to go up, then the key value for the action of up is higher than going down or a no-op. Likewise, right here, it's really important to go up, and so the key value is higher for going up than the actions of going down or no-op. In the right case, it doesn't really matter because the ball is on the other side, on the opponent's side, and so the key values are more uniform. So when you visualize these key values, they look pretty reasonable, which is good. But then if you actually plot like what the true returns are, the true returns are shown in red here on this red horizontal line, and the estimate of the values according to the Q network are shown as this upper line. And you actually see this really huge gap between the estimate, where the estimate is always a lot higher than the true value. And so it seems like we're seeing a lot of what's called overestimation, where our Q function is overestimating how good our policy is. And then there's this algorithm that was introduced called double D2N that's able to get a much more accurate Q function, and is able to overestimate far, far less than D2N. So let's talk a little bit about double D2N. So, and overestimation in general. So our target value is, we're taking a max over action right here. And when we take this max, we're choosing an action that maximizes this p-value. And you can, another way to write this is you can think of it as, I might need a little bit. You can think about this quantity as Q of phi of f evaluated at the action that is maximizing our Q phi. And so we're both choosing an action that has a high Q value and evaluating the Q value of that action using the same Q function. And this means that if there is noise in our Q function, then it's very easy, this noise is very easy to basically pick actions that are using that noise to get a higher Q value. And so this last term right here is what's causing overestimation. It's not perfect, it has some noise in it, as neural networks generally do, and because the action selected according to Q is the same as what's being evaluated, then you can really exploit that noise and choose actions that have higher value than they actually do because of the noise. Now, if you instead used a different Q function for picking an action and evaluating it, then you could decorrelate the noise. If you had two different Q functions, they would have naturally different noise and different errors if that makes sense. And so if we have a way to use different Q values, we can actually then eliminate this problem of overestimation by essentially decorrelating the noise by using a different Q function to pick the action here as to evaluate the action. And so the key idea behind double Q-learning is to use two different networks. One network, network A, for picking the action, and network B for evaluating. And then if they're noisy in different ways, then we're not going to then be kind of exploiting noise in our Q-values. And then as a result, not overestimating our Q-values. The question is, can you guarantee that they don't have the same noise? I guess you definitely can't guarantee it, and there might be some noise that's a result of the architecture of the network. But in practice, this ends up making a really, if you are using different neural networks for this, it generally does a very good job. There's still some overestimation, and if we looked at these values, like here in this game, the Q values are still an overestimate here, and also here as well. But it helps substantially compared to not doing it. So it's not perfect, but it helps quite a bit. The question is, what if you did triple DQN or quadruple DQN, use even more networks? It's a good question. I could see that, perhaps that if the noise correlation, if you're able to get even more samples of noise, that could help. It could be interesting to try that in practice if the noise is coming from, if it's instead coming from a source that's kept constant, like the architecture of the neural network or something like that, then it might not help until you start to introduce those. And then in practice, using more than two neural networks is very effective. How do you ensure that they don't diverge? So let's actually talk about what we actually do. So we're actually already using two neural networks. We have the current neural network and the target neural network that was just periodically frozen. And so what we can actually do is when we do our Q updates, we can use the target network, Q5 prime, for evaluating, and the current neural network for picking the out. So that's essentially what double Q-learning looks like, where instead of using the target network for both of these, we're going to use the current network to pick the action, pick the best action, and then the target network to evaluate. Yeah, so your previous Q is always going to be your previous Q, and so you can't measure it yet. Yeah, so the question is, why does this help, especially if the previous Q has the same noise? So the previous Q will be outdated, and the new Q will have gotten a lot of gradient updates since then. And so, and they've seen new data points recently. And so, oftentimes the noise isn't just about initialization, but it also has to do with what gradient updates were applied. And so, yeah, it helps. Okay, the last trick we'll talk about, which we've already talked about in actor-critic methods, is n-step return. So our Q-learning target looks like this, with the reward plus the max of Q. If your Q values are good, then this term is actually going to be really, really important in playing most of the roles in the Q-learning update. But if your Q function is bad, at the beginning of training, then these are really the only values that are going to matter, and these are the values that are going to be getting your learning algorithms picked. And if you just have a single reward function here, then that might be a bit troublesome, because just a single reward function might not tell you that much about how good your Q value is. So if you remember when we talked about actor-critic methods, we talked about using n-step return. So if we use this Monte Carlo, we would use the sum of rewards. If we use bootstrapping, we just do R plus V, the R at the current time step plus the V at the next time step. And instead, we talked about this thing that we could do in the middle, where we sum the rewards over the next n time steps, and then use the value at the time step after that. We talked about how this has less variance and lower bias, in the sense that if your targets are bad, the reward function is going to be more accurate. So can we do this for Q values? And what this would look like for Q values is, instead of having something like this, say this is the target for you're trying to get the target for SPAP, then you would define yi to be r at the current time step plus r at the next time step up until r at t plus n minus 1 time step. And then at the time step after that, use the max of q of st plus n a t plus n, where this maximization is over a t plus n. So this is what n-step returns could look like for Q-learning. Does anyone see any potential issue with using this target? Yeah, so if you're doing this off policy, these R's will be coming from whatever policy you used in the replay buffer, rather than the optimal policy, which is what you're trying to estimate the Q. So there's kind of pros and cons here. One is that it's a lot less biased, a lot faster to learn on, especially early on. But the downside is that these rewards are for the policy that collected the data, not for the optimal policies. And we're trying to estimate the key function for the optimal policy. So this is a kind of a downside when using n-step returns with learning. Now, and this is not an issue with n equals 1, because there the reward will just be a function of s and a, and we're estimating the q value of s and a. Now, what do we do about this? Maybe the unsatisfying answer is that most commonly just ignore this, pretend it isn't true, and still use an n greater than 1. And n-step returns truly are often very often improve the performance of the algorithm, despite being incorrect. That said, there are other things you can do. You could dynamically choose n and only use data that follows the current policy. Basically looking at what actions were taken and seeing if those actions actually agree with the maximal q value. You could also, in principle, dynamically choose n and have n be smaller later in training, where your q values are likely to be more accurate. Now, for this particular choosing of n, you really would want to do this only if the action space is small and the data is mostly on policy. And you can also do important sampling as well, and weight these rewards by some importance. Great, so those were the kind of 3 tricks for Q-learning in practice. There's a couple examples of Q-learning that have been very successful that I put on this slide. I think there's other examples too, but one of the most prominent examples was for playing games. And if you want to train an agent to play a game, either just for the sake of seeing how well you can do, or to play against a human, Q-learning was able to outperform most people on Atari games. So this bar right here is everything above this bar are the games that it is at human level or above human level performance, and everything below is worse than human level performance. And then it also was used to train a robot grasping system. So this is actually a case of continuous action, and the robot on the right is using a Q function that was trained with Q-learning, and then it is doing a kind of a continuous optimization over actions that will try to find a good way to grasp the object. And we talked a bit last time about how with RL you can get much higher success rate and more reliable policies, and we see that here too, where this system was able to get a 96% success rate, so quite high at being able to grasp objects. The other thing that's nice about using RL for this application is you end up if in order to graph you need to not just go down and pick something up, but you actually need to move around the object. It's also able to learn how to do that using the reinforcement because it's treating it as sequential procedure. I think that one of the last things I figured I would cover is some of my advice on when to use one online RL algorithm versus another, since this is the last online RL method that we'll talk about. So we talked a bit about CPO, SAT, and DQN. Those are like some of the three main technical algorithms we talked about. For PPO, this is great when you care about stability and ease of use. Generally doesn't require too much tuning, but it's very data inefficient. And so it's great to use when you care about stability and ease of use, and you don't really care about data efficiency. DQN works quite well when you have discrete actions or low-dimensional continuous actions. And so in those cases, it can be a great choice. It can be fairly data efficient, depending on some of the details and how off-policy you make it. And then soft actor-critic and variants of it are great when you care most about data efficiency, but require a bit more tuning and are a bit less stable than something like CPO. So what we talked about is QNing, also QNing in practice, the three tricks with target networks, double DQN, and step returns. We defined it like the Bellman equation and the Bellman optimality equation. And that was like essentially an overview of how to do RL without learning an explicit policy. We're done with online reinforcement learning algorithms for now. We covered a lot of the basics of different online reinforcement learning algorithms.